Welcome back to mass transfer operation 2 course. In the last class we discussed on membrane separation processes. Now we will start the new topic adsorption and ion exchange. The syllabus is as follows. Firstly, we will be discussing on adsorption and types and nature of adsorption, then adsorption isotherm. Then we will be discussing on stage wise and continuous adsorption processes. Thirdly, we will be discussing on fluidized bed and teeter bed, steady state moving bed adsorber, and finally, we will be discussing on unsteady state fixed bed adsorbers and the another new topic, that is ion exchange. Okay. So, now we will be discussing on the basic knowledge about this adsorption, then types and nature of the adsorption process and adsorption isotherm. So, in the beginning we need to understand the phenomena this adsorption. This is one of the mass transfer operations, and previously we have learned in mass transfer operation 1 the process absorption AB. So, there we have learned that the absorption process was the bulk phenomena. This particular component or target component absorbed inside the core of this absorbate, and so that time we assumed that the surface of the solid material or a particular component is not contributing towards the separation of the target component. But now we will be discussing the new separation process, that is adsorption. So, adsorption is defined as the selective concentration or retention of one or more components of a mixture on the solid surface. Like this, if we say this is the solid surface, and say on the solid surface, at the outer surface of the solid, suppose the gas molecules are trapped. So, only at the outer surface this gas molecule is not entering inside the interior of the solid surface. Then on the top surface only the gas molecules are we can say absorbed, or we can say this one are sticked. Then we can say this is the phenomena of adsorption. Okay, so, adsorption on a solid surface occurs due to the affinity of the surface for the particular substrate. Okay, so, there is a interaction between the solid surface and the target component. So, if they are compatible to each other, then only we can say target solutes, or we can say whether it is a gas or it is a solid or any liquid, that will be sticked on the outer surface of the particular solid material, and this will be separated from the system. Like if we say activated charcoal, so this one on the activated charcoal, say suppose say few gas molecules need to be separated, then we put this one, and then say gas molecules will be sticked on the top surface of the we can say activated charcoal. Once the we can say the all the active sites, or where the interaction of the gas molecule will be there with the top surface of the activated charcoal, then these will be sticked, and then it will make the say layer like this one, and then we can say we can separate these solid activated charcoals from the system to separate the particular gas molecules. Okay. So, selectively we can say separate a particular target component from the mixture. Okay. So, we need to now learn the few terms like this. Firstly, we say adsorbent, that is the solid substance that adsorbs a component is called this adsorbent. Like this, if we say any charcoal, or we can say this, so many adsorbents are there. So, we can say this is a solid substance where the particular target component is sticked on the surface only. So, that we can say adsorption is a surface phenomena. On the surface only, when the active spaces are available, these spaces can target or trap the solutes or target components, and then these are separated from the system. Now, the adsorbate, the component, or we can say this one target component adsorbed is called adsorbate. So, this is the target component, or which one is of interest to separate from a mixture or a selectively separation of a target component is called adsorbate. Now, we say this another terminology we should learn this one, that is called absorption. So, selective transfer of the molecules of a mixture to the surface or into the bulk of the solid. So, whenever we discussed the absorption process, we discussed that the particular target component, or we can say this one maybe a target component or a mixture of target components that enters into the bulk. So, that was absorption, and so that is absorption. Whenever we say this one to the surface, that is we can say this one adsorption. So, this combination of adsorption and absorption. So, we can say this one AB plus AD, and then we can say this one absorption. So, in as a whole we can say that is the absorption. So, this combination of absorption and adsorption is called absorption. Okay. So, now we say this one schematically we can say that suppose this is the active charcoal site, and say at the top only we can say this a particular target gas component is we can say this one adhered. So, that is we can say this one adsorption process. Like if we say any, so suppose photocatalyst like one adsorbent is there, the solid material, and we want to this one separate the say dye molecules, then these dye molecules will be sticked on the surface only of this we can say this one photocatalyst. So, that dye molecule actually will not be entering here. So, that is why we say this is the adsorption phenomena. Okay. Then we can say this one we need to understand the types of adsorption processes. So, there are two different types of adsorption processes. One is this physical adsorption, or we say in simply we can say physisorption, or in other words we say van der Waals adsorption. So, and another one is called chemical adsorption or chemisorption. Now, we need to understand the process of physical adsorption or physisorption. So, that is we can say reversible phenomena which is a result of intermolecular force of attraction between these molecules of the adsorbent and say this adsorbate. Okay, so, the adsorbent and adsorbate. So, like we can say only van der Waals force of attraction, or we can say only intermolecular force of attraction takes place, and there will be no chemical reaction or any bond formation. That is why physisorption process is called a physical phenomena. Only the molecules the target components will be sticked on the say adsorbent only due to their interaction only in the we can say the molecular level. So, no sharing of electrons or bonding takes place in case of the physical adsorption or physisorption process. Okay. And whenever we will be talking about chemical adsorption or chemisorption process, so this is an irreversible phenomena which is a result of bond formation between atom of the adsorbent and adsorbate. So, there is a real bond formation between this one. So, we can say whenever a target component comes into the contact of this adsorbent, then there is a chemical reaction and bonds are formed, and finally, these are converted into the particular product. So, we can say suppose if we say different, we will be explaining few examples also where the chemical reaction takes place and followed by the we can say the occupation on the top surface only. Then we can say these are chemical adsorption process or chemisorption. In chemisorption, we will be landing up with a new product. Suppose we have one target component, we have one adsorbent. So, adsorbent adsorbate interaction will be there, will be chemical reaction, then new product will be formed, and that will be separated as a whole. And whenever we will be trying to get back that target component or adsorbate from the system, so it is not possible in most of the cases, or we can say this reversible reaction may not take place in many cases. But in case of physical adsorption, so as these are only physically these are sticked due to their intermolecular this one interaction, So, these are we can say only the physical phenomena. Whenever we will be doing the reverse of this physical phenomena. So, that target component which is sticked on the this on adsorbent surface is coming back to the system very easily. So, there are differences like this we can say in case of physical adsorption or physisorption process, weak van der Waals force of attraction between the adsorbent is there. But in case of the chemisorption, chemical bond formation takes place, or we can say this new product is formed. So, as this is a physical phenomena, so it favored at the low temperature, but so as this is a chemical reaction this one takes place. So, that is why we can say this one it is favored at high temperature, or maybe the activation energy will be higher in case of the chemical adsorption process. So, it is not that it is always will be favored at the higher temperature. If it is endothermic reaction, so it will be favored at the lower temperature also, but we can say this one but the extent will be higher than the physical adsorption. Okay, so, then activation energy is not required at all, because it will be this one adsorbent will be interacting due to their intermolecular force of attraction, but in case of the chemical adsorption or chemisorption, the activation energy is required. And as this is a physical process, so this is a reversible process. Just if we change the operating conditions, then we can say if we do the pressure swing or temperature swing desorption process, it will be separated very easily, but in case of the chemical adsorption process, in general it is irreversible in nature. That is why we will not be getting back the target component. So, no low enthalpy of adsorption, in general we can say this one, this is we can say less than 10 kilocalorie per this one mole, and so in case of this chemical adsorption process, it is greater than we can say 20 kilocalorie per mole. So, this is non-specific, only we can say this it is coming, and we can say coming in contact with the adsorbent is coming in contact with the adsorbent, and these are sticked on the surface. But in case of the chemical adsorption, very specific in nature, means say it should be compatible, or we can say this one any chemical reaction should take place. That is why you can say this is a specific in nature. Then multi-molecular layer on the adsorbent surface may be this one formed, or we can say this one, as this is the only due to the intermolecular force of attraction. When one layer of the adsorbent is formed, then that adsorbent will act as the new adsorbent for the rest of the molecules. So, then again the adsorbent will be sticked on the surface. Suppose this is initially the adsorbent, and then suppose new layer actually of adsorbent is there, and now so it is acting as the new adsorbent for the others, then these will be formed like this, because these are due to the intermolecular force of attraction. So, these are actually coming, and layer by layer actually these will be formed, and for the new this one adsorbent, it will be acting as, so both this the actual adsorbent plus the layer will be acting as the new adsorbent for the other molecules like this. But for chemical adsorption, it is in general it is a monolayer, because this one once suppose on the adsorbent surface one will be reacting, then it will be destroyed. So, there will be no other space to react. Say suppose one new layer actually will be formed, then it will not get the fresh molecule to react with the other adsorbate. So, there we can say this one, this is monolayer, this one what is called adsorption process. And we have so many commercial adsorbents, and their applications also are diversified. The most common one is activated charcoal, so or we can say activated carbon. So, it is a microcrystalline this one graphitic form of the carbon. So, there are two different types of we can say carbon activated carbons or charcoals are there. So, one is this PSC and another one is GSC. We can see this powder activated carbon and granular activated carbon. So, in case of the powder activated carbon like this one, so it is we can say highly powdered material, and sometimes the powders are in the nanometer range also, and that is why the specific surface area or surface area per unit mass also is very high. and there are several applications like this decoloration of the fruit products, then sugar refining, then wine production, then water treatment like this for drinking water. In most of the domestic water purifiers, they use these powder activated carbons as the one of the primary this filter medium, and this can purify both the, we can say, suspended material as well as this odor or smell, and refining of the vegetable oils and the fats. And the second one, that granular activated carbon. So, the granule size of this in the millimeter range. So, these are there, their specific surface areas are to some extent lower than the powder activated carbons, because the sizes are big, that is why specific surface areas are less. So, the applications are solvent recovery from the vent gases like alcohol or ketone, then air purification, then flue gas desulfurization. There are so other applications also. Then the next one is the molecular sieve, or we can say synthetic zeolite. So, that is also widely used. There are also two different types of synthetic zeolites. So, these are crystalline and aluminosilicates of metals like sodium, potassium, magnesium and calcium. So, starting materials for zeolite preparation are sodium aluminate, then silicate and hydroxides or alumina trihydrate like this Al2O3, 3H2O, then colloidal silica and silicic acids. So, reaction of the ingredients is followed by gel formation under the controlled condition. So, that actually happens for the formation of the molecular sieves, and then gel is crystallized slowly, and then crystal is filtered, then washed, then ion exchanged to replace the sodium with suitable cations, because in the beginning sodium or potassium ion was there, and this is replaced by a suitable cation like this. So, that type of say metal ions are required by this ion exchange process. Then these have both the adsorption as well as catalytic properties. So, most of the molecular sieves like this, so these like type A or type X both have these commercial applications. So, the commercial molecular sieves are generally of type this one A and X, like 3A, 4A, then say 5A, and type X is 10X, 13X or so many others also, say XAD 7, 3, 5, 10 also, these are all there, all these are molecular sieves. Like this, suppose for zeolite A, that type of structure is there but in all the cases we can say the distance between the layers are around say 12.3 angstrom for zeolite A as well as this for zeolite X also. Okay. So, these are used actually for separation of aromatics, then used as the catalyst in so many reactions, depends upon the ability of selective adsorption also, because it is a size based separation, as the we can say the different openings are like this is the opening of one zeolite. So, it can trap a particular say material with this particular suppose hexagonal shape. Here also this is one opening, like this one based on there is another opening. So, in this side there is one opening. So, based on the opening size we can say the particular target component will be trapped inside this one, and whenever we will be doing any pressure swing or temperature swing desorption, it can release very easily. And this is also used for the removal of water and carbon dioxide from the gas, or we H2S from the natural gas, then mercaptans from the petroleum fractions also, and these are also used for the separation of normal paraffins from their branched or cyclic counterparts also. Because as these are of different specific sizes, then the target components with that similar shapes will be trapped inside this particular type of the this we can say zeolite. Then third one is this silica gel, that is also widely used, but it is very hydrophilic in nature or hygroscopic and very polar material due to the presence of this hydroxyl group. Like this one, say if I say this one the network structure of silica gel, so we will find so many OH groups actually present in the silica gel. Okay, so that is prepared by reacting this sodium silicate NiSiO3 with the sulfuric acid to get silicic acid, then followed by the dehydration we will get the silica gel. So, that silica gel actually, as it is devoid of water, so it can trap water very easily. So, that is why in most of the cases the silica gel is used in so many electronic devices as the dehydrating agent. So, this is a good adsorbent and it can trap water very easily, and its capacity also is very high. So, silica gels is of two types like this, A type and B type. So, in case of the A type, we can say this one 2 to 3 nanometer size. So, very small sizes, that is why specific surface area is very high, that is 650 meter square per gram. Whereas the B type has this diameter is very high, means greater than 7 nanometer, that is why specific surface area is very low. Okay, so, the application is drying of air and natural gases, then drying of liquid hydrocarbons and other gases, and also it is a dehydrating medium for the so many electronic devices like we can say these desktops or any say we can say television set or so many electronic devices, there silica gels are used. Then the other one or fourth one is activated alumina. This is also widely used as the adsorbent agent, or it is used as the good adsorbent. This is basically a highly porous gamma alumina. It is manufactured from precipitated aluminum hydroxide gel. Okay, so the pore size ranges from 1.5 to 6 nanometer, and specific surface area is not so good, only 200 to 400 meter square per gram, but bulk density also is very high, 700 to 900 kg per meter cube, and porosity is almost in the 40%. So, that is why this activated alumina that is used as the good adsorbent. Applications are like this, dehydrating agent for both gases and liquids, because that can trap also water molecules, then drying of air like this for air liquefaction plant, and hydrocarbons, then sulfur dioxide, then few refrigerants, this on drying of the kerosene, then gasoline, then different aromatics also. Now, we will be discussing about the characteristics and properties of the adsorbents. First one that actually is important is the selectivity. Means whenever in the beginning also we discussed that the adsorption process is entirely dependent on the adsorbent adsorbate compatibility. So, there the selectivity plays an important role, means it should be this adsorbent should be selective towards the adsorbate. Otherwise, this the separation during this adsorption process will not be economic also. So, selectively binding of the target component is the prime factor to use this adsorbent as the suitable this one separating medium in a we can say this one adsorption process. So, then adsorption capacity that should be also very high. So, it is actually dependent on the specific surface area as well as the we can say the active surface area. So, should be very high, so that this adsorbent requirement will be very low, or we can say this one for a particular application we need to handle very less amount of the adsorbent, and so that will be another factor also. And the third criteria will be like this, reversibility of the adsorption process. We say this one is called this desorption process. We will be discussing this one also in detail. So, for recovery of the adsorbate and reuse of the adsorbent. So, whenever we will be trapping one adsorbate from the mixture, so how easily we can separate this one from the adsorbent. If there is a very good compatibility and the adsorbent is not ready to release the adsorbate, then we can say this adsorption process may not be we can say economic also, because once it is separated due to this trapping, it should be separated also very easily by applying the we can say different techniques. Then particle size and in distribution, if we say if the particle sizes are very fine, or we can say this one nano size particles, then specific surface area will be high. As the adsorption process is a surface phenomena, with the increase of this surface area, their adsorption capacity will be very high. And at the same time, if the particle size distribution will be in the narrow range, then we can say that is good for a we can say this one as the adsorption process, because the target component will be of the similar type. So, that is why it will prefer the similar environment. Okay. Then we will be thinking of the porosity and pore size distribution, that will be highly porous. So, that we can say this one surface area, that is exposed surface area should be very high, and narrow pore size distribution will be always preferable over the wide pore size distribution. In case of the wide pore size distribution, most of the say pores with very big size or small size will not be utilized for a particular we can say component trapping. And then specific surface area, that is we can say this one surface area per unit mass, that should be very high. And the last one, that is called structural strength and stability, that should be one of the criteria, that once the adsorption process is over, we need to separate the adsorbate adduct, and that should not break during this handling, or we can say once the process is over, we need to separate this adsorbate from the adsorbent, and then we need to reuse this one for the next adsorption process. So, if these are not stable, or we can say if these are brittle in nature, then with time the size reduction will take place, and at the same time we will be landing up with another problem, that is handling problem, because if these are converting into very finer particles, then the separation of the finer particles will be a problem also as the adsorption process progresses. Now, we will be discussing one important term, that is adsorption equilibrium. So, we can say this one, once this adsorbent and adsorbate are in contact, then we can say this one adsorption process will take place in the beginning very fast, but at the same time the desorption process also will be occurring there. So, but you see in the beginning adsorption process will be very fast, but desorption process will be very slow, and we can say this one whenever the fresh adsorbents are there, we can say this one bare surface is there and exposed surface areas are more, we can say then there will be good interaction between the adsorbent and adsorbate, and we can say this one, that is why rate of adsorption will be very fast. But at the same time we can say in the beginning rate of desorption will be very minimum, but once the adsorption process is over, then the desorption process will start. That time we can say whenever desorption process will start, that time desorption process will be proportional to the adsorbed surfaces only. But in the beginning when adsorption process was there, that was proportional to the vacant spaces or unadsorbed spaces, because if the unadsorbed spaces or vacant spaces or available spaces are more, then adsorption process is very high. So, these two phenomena are entirely different. Adsorption process is proportional to the open spaces or unadsorbed spaces, but desorption process is proportional to the desorbed or vacant, or we can say this occupied spaces. Okay. So, at a constant temperature, amount of adsorbed per unit mass of the adsorbent depends on partial pressure of the adsorbent in the gas phase or concentration in case of the we can say this on solution. So, the equilibrium relation between the amount adsorbed Q and the we can say this one concentration C of the adsorbate or solute actually at a constant temperature T is called the adsorption isotherm. So, when we can say this one adsorption equilibrium is reached, or we can say this when the rate of adsorption and rate of desorption is same, that time we can say the relation between these between this amount adsorbed Q with the we can say concentration of the adsorbate, that is we can say the relation is called adsorption isotherm, that is given by Q is the function of C. Okay. So, there are 5 different types of adsorption isotherms. So, the first one is we can say the type is we can say this one, say suppose with we can say P by PV, actually we see this one the moles adsorbed, or we can say this whatever Q we say, that is increasing very fastly. So, that is we can say this one type 1. So, that is we can say this one very favorable one. So, like oxygen adsorption on the carbon block at minus 183 degree Celsius on the concave downward, that is we can say this very favorable one. Then type 2, that is we can say this one BT type, like say for multilayer this adsorption of water vapor on the carbon block at 30 degree Celsius. So, here also you can say this for BT it is also a favorable one. So, if we increase the P by PV, so we can say this one moles adsorbed or say capacity will go on increasing. So, in the beginning say maybe the increase will not be so high, but after a particular point this increase will be very fast, we can say exponentially it will grow. Then type 3, that is also, that is called, this is one is unfavorable one, like adsorption of nitrogen on the ice, means with increase in the partial pressure the moles adsorbed or capacity is growing exponentially, that is you can say exponentially, but that cannot be favorable one, or realistically we can say it cannot be happening, because we discussed this one in the beginning also, that it is a surface phenomena, and in the beginning that rate should be very high like type 1, but with time this rate should decrease, but it is showing that reverse one. In the beginning rate is very less, but whenever the surfaces are adsorbed then the rate is increasing very exponentially, but that is unlikely, that is why it is unfavorable one. And the type 4 and 5, these are there like alternating convex and concave, like this one, like this is suppose concave then concave, or this concave convex concave, or we say the concave convex concave, like this different types of are there, been alternating convex and concave type will be there, like capillary condensation say within the pores. So, these are type 4 and type 5. So, out of this we can say this 3 is not favorable, which is exponentially increasing with the increase in the partial pressure, or we can say this one with the increase of the solute the target components or adsorbed concentration in the system, that is not we can say favorable, but BET also is favorable this one for multilayer adsorption process. Now, we will be discussing few of the isotherms. This most common isotherm is Langmuir isotherm. So, that is widely used. Scientist Langmuir actually first observed that type of adsorption behavior, and after his name this isotherm is this one termed as Langmuir isotherm. But for that say few assumptions are there, like this molecules are adsorbed at the discrete active sites on the surface, then each active site adsorbs one molecule only, and so that is why we can see the energetically all the active sites are equivalent like this, and adsorbing surface is energetically uniform. There is no interaction among the adsorbed molecules like this, but it should not be. Whenever one molecule will be taking one particular place, whenever in the periphery, when other molecules will be coming, definitely this will interact, but we are ignoring that interaction among the adsorbed molecules or adsorbates. So, that is why, so as a result the rate of capture of the molecules of the surface is proportional to the uncovered area, so 1 minus theta, and the partial pressure of the concentration. So, that is why we can say this rate of adsorption process is equal to say K1 into P into 1 minus theta, that is definite one. So, we can say whenever we will be talking about this, so rate of adsorption that proportional to, we can say this with the uncovered areas. So, we can say this theta is, we can say covered area, and that is why this rate of adsorption that is equal to say K1 into say partial pressure. If it is a gaseous one, if it is liquid, then it will be concentration. And whenever we will be talking about rate of desorption, so that I told that it is proportional to how much amount covered area is there, means how many molecules are now occupied or adsorbates are occupied in the adsorbent side. So, that is why rate of desorption is proportional to theta. So, then we can say this equal to, we can say K2 into theta. Okay. So, we can say this one at equilibrium, we can say, so rate of adsorption will be desorption rate. So, that is the definition of we can say this adsorption equilibrium. So, then we can say K1 into P into 1 minus theta is equal to K2 into theta. From here we will be getting theta is equal to say theta will be equal to capital K into P by 1 plus capital K into P, where capital K is equal to K 1 by K 2, or we can say this one sorry, rate constant between the adsorption and desorption process. Okay. So, this theta is equal to we can say K P into 1 by capital K into P, where we can say this theta is equal to say Q by Q max, we can say that is equal to capital K into P by 1 plus capital K into P, or we can say Q is equal to Q m into capital K into P by 1 plus capital K into P. So, this equation is called say this Langmuir isotherm. Where this Q is equal to we can say this an amount adsorbed per unit mass, whereas Q m is the we can say this one maximum capacity. So, this Q equal to we can say this one amount adsorbed per gram adsorbent and Q m is equal to maximum quantity of say gas or adsorbate or whatever may be adsorbed per gram adsorbent. Okay. So, at very low partial pressure, or we can say when the adsorbate content is very less, then what will happen, this in this equation say we can say this K P that will be we can say much lower than 1. So, the whenever P is very less, then what will happen, this Q will be equal to Q m. So, K P will be much lower than 1, means then will be like this Q m into K into P. That will be, so this Q m into P we can convert this on into K H into P. So, I think we know all these, this H is we can say Henry's law constant. So, this K H is this Henry's law constant. So, it is like we can say it is a linear one, we can say, then we can say so this equation is the form of we can say linear isotherm. So, we can say whenever at low P, it is a linear form of the linear isotherm. Okay. And say we can say this one at large P, we can say capital K into P will be much greater than 1. Then will be Q will be like this, Q is equal to we can say Q m into K P by K P. Okay. So, that will be like this, Q will be equal to Q m, that is equal to Q m. So, that is we say whatever theta we say this one, or so that is will be equal to say we can say this 1. Okay. So, Q is equal to, so Q is equal to Q m into K P by K P, that is will be equal to say Q m, that is we can say this one is equal to then we can say this one, this theta will be equal to 1. Okay. So, Q by Q m is equal to theta is equal to 1. So, we can say, so that is we can say this one form where will be maximum amount adsorbed per unit mass of this adsorbent will be this only unit, or we can say this one was 1. Okay. Now, we can rearrange the Langmuir equation, say q is equal to q m into capital K p by 1 plus K p. So, in the linear form, in the say we can say this one in the linear form, it will be like this p by q is equal to 1 by q m into K plus p by q m. So, this is a linear, just if we do the manipulation, we will be getting like this one, and then we need to plot this p by q versus we can say this one, if we plot p, then we will be getting one, just it is we can say y is equal to m x plus c. So, then we can say this intercept, that is will be equal to we can say 1 by q m into K. The intercept will be 1 by q m into K, this one m x, this one, and slope, this m will be, slope will be say we can say 1 by q m. Okay. So, now we have slope by intercept is equal to 1 by q m divided by 1 by q m into K. So, that is we can say it is coming out as 1 by q m, 1 by q m, that is say K. So, slope by intercept actually will give this K is nothing but K 1 by K 2. Okay. So, from there slope by intercept will be getting this capital K. Okay. So, that will be getting. Okay. So, then the another important isotherm is we can say this Freundlich isotherm. So, this is an empirical isotherm actually, which assumes that the amount adsorbed at equilibrium has power law dependence on the partial pressure. So, whatever the equation actually we have now derived, say suppose for this very low pressure, like this we have this q is equal to K into P. So, for this we can say very low pressure like this using this Henry's law type equation, q is equal to K p into P. Here it is K prime into P to the power 1 by n. Okay. So, if I take this logarithm of this equation, then we will be getting ln q is equal to ln k prime plus 1 by n into ln p. So, these parameters k prime and n actually are called adjustable parameters, as these are all empirical, this is empirical relation. So, we can say this k prime and n, this can be obtained very easily from the experimental data points. So, this we can say these are all adjustable parameters, and adsorption on the surface is energetically non-uniform. As a result, the heat of adsorption at different sites actually is not same. And whenever we will be plotting this equation, like here also y is equal to side like mx plus c. So, we will be getting intercept as we can say this one ln k prime, and slope as this we can say this 1 by n, like this m will be 1 by n like this, because we have plotted with ln p versus ln q. So, log plot of this Freundlich equation will give a straight line, and slope will give this 1 by n, and intercept will give ln k prime. So, directly from the slope we will be getting n, and from the anti log of this intercept will give the k prime values. Okay. Then third one, this one we can say this for the n values actually varies between 1 to 5, and for n is equal to 1, Freundlich equation transforms into Henry's equation, that we have seen this one. Say suppose say q will be equal to k into p, because this one k h actually is there, k h into p to the power 1 by 1 like this. So, will be like this, q is equal to k h into p. So, Freundlich isotherm is practically useful and can fit many experimental adsorption data points also. We will be solving few problems, and this will fit this one in a very good extent for so many applications, or for so many industrial these adsorption processes. but it is thermodynamically inconsistent in the sense that it cannot give a finite value of Henry's law coefficient, that is kh value, this one as concentration or partial pressure tends to 0. Whenever we can say this one P will be tending to 0, that time actually we can say this one Henry's constant coefficient or kh value will not be getting a finite value. That is we can say inconsistency in terms of the thermodynamic consideration. Then another isotherm is that, though it is not widely used, that is Dept isotherm. So, it is also an empirical isotherm useful for the correlation of equilibrium adsorption data on heterogeneous adsorbents like activated carbon. So, there the equation is like this, Q is equal to Q m into P by B plus P to the power n whole to the power 1 by n, where this Q m, B and n, all the three parameters actually we can say these are all known parameters that will be obtained for a particular adsorbent adsorbate couple. And say we can say this one Valenzuela and Meissers used this isotherm to correlate the adsorption data for a large number of systems in 1989, but nowadays also many systems follow this Dept isotherm as it is a one empirical isotherm. So, that is why in many cases it will fit very well. And then another one isotherm is this BET equation or isotherm under the after the names of the three scientists, this Brunner, Emmett and Taylor. Okay, so, the BET equation represents this multilayer adsorption equilibria for many systems. The equation is given as this Q is equal to Q m into C prime by 1 minus x into 1 plus C prime minus x 1 into x, where this Q m actually is the quantity of the gas to be adsorbed to form monolayer. But in case of the other adsorption isotherms, that Q m represents the maximum adsorption capacity. So, we need to remember this one whenever we will be plotting the BET isotherm, the Q m will be this amount adsorbed for this monolayer formation. Okay. And where this x actually is we can say this P by PV. So, that is we can say this one partial pressure by vapor pressure. So, this x actually the fraction, and C prime actually we can say temperature dependent constant for particular gas solid system. Whenever we will be solving the problem, we will be discussing all this in detail. And for BET isotherm, we need to assume that heat of adsorption remains constant till the formation of monolayer is complete, and then for secondary layer heat of adsorption is assumed to be equal to heat of the liquefaction of the adsorbate. So, that is another assumption also we can say. Now, we will be determining the specific surface area of the solid for this BET adsorption. Okay. The projected area alpha of an adsorbent molecule can be calculated using this equation. This alpha equal to 1.09 into m by n into rho to the power 2/3, where this m is the molecular weight, this n is the Avogadro number, rho is the density of the adsorbate. So, and then will be this one the specific surface area. We know that we can say this this specific surface area Sg is obtained by using this equation that we have already derived this one, this into alpha, where the specific surface area Sg is equal to Qm, that is how much amount adsorbed for making monolayer, n is the Avogadro number, and alpha is this we can say this one the projected area. Okay. So, now say we need to calculate this Sg. For that actually we need to calculate this x will be calculated as this P by PV in the this one BET equation. So, this in this BET equation, this Q is equal to Qm into C prime by 1 minus x into 1 plus C prime minus 1 into x. There will be putting this x is equal to P by PV. Okay. So, then we will be getting this P by Q into PV minus P, that will be equal to 1 by C prime into Qm plus C prime minus 1 into P divided by C prime into Qm into vapor pressure. Okay. Now, we have this one, we have this, we can straight line equation. Okay. So, what we will be doing now? We will be plotting this P by PV versus this P by Q into PV minus P. So, this y versus x. So, y is equal to, say we can say mx plus c. Then we have also now this intercept is equal to, we can say intercept is equal to 1 by c prime into qm, and the slope will be, slope is c prime minus c by c prime into qm, okay, qm, this p by pv. So, then we have this, we can say the, we will be now doing this one, we will be doing this slope plus intercept. In case of this VT, we will be adding this slope and intercept. So, now we will be getting like this one will be equal to c prime minus 1 by c prime into qm plus intercept is 1 by c prime into qm. That will be giving as c prime this 1 by qm prime minus this one. So, 1 by qm. So, this slope plus intercept will give this 1 by qm, then we can say this qm, this how much amount of this one solute actually or adsorbate will be forming this monolayer, that will be 1 by slope plus intercept. So, that is we are now we are able to get this one. Okay. So, once we get this one, so from there actually we can say this one Sg will be getting, once we have this qm. So, then we will be getting this, suppose this we know this now Sg is equal to the specific surface area is equal to qm, we will be getting just by this reversing this slope and intercept, slope plus intercept. So, we will be getting this, we have this qm and we know this this Avogadro number and then alpha. So, now we will be able to get the specific surface area. Okay. Now, we will be discussing this another isotherm, that is Schiff's isotherm, though it is not widely used, but in some cases we can say this one, if we combine the Langmuir and Freundlich isotherm, we will be getting one another isotherm. This is we can say also a empirical isotherm. Q is equal to qm into k double prime into p to the power 1 by n by 1 plus this one k double prime into p to the power 1 by n, where this qm is the, we can say this one adsorption maximum adsorption capacity, k double prime is affinity coefficient, and n gives the measure of the system heterogeneity, that is also we can say this one a constant for a particular system. So, it is one empirical isotherm. Now, we will be discussing about the heat of adsorption. So, there are three different types of heat of adsorption values. One is the differential heat of adsorption, then second one is integral heat of adsorption, and third one is isosteric heat of adsorption. Out of this, we will be more interested in the isosteric heat of adsorption. So, in case of the differential heat of adsorption, rate of change of the integral heat of the adsorption with adsorbent loading will be there. For the case of the integral heat of adsorption, total enthalpy change from 0 adsorbent loading to the final loading at temperature T will be there. And for isosteric heat of adsorption, similar electronic arrangements of the chemical compounds, that is active sites, are energetically homogeneous, we assume this one, and heat of adsorption is independent of adsorbent loading. And when the temperature will be changing, for calculating this isosteric heat of adsorption, we need to change the temperature from T1 to T2, and that time actually we will be getting this one. We will be calculating the from the thermodynamic consideration. Okay. So, that we will be doing like this one using this Clausius-Clapeyron equation. So, like this if we say the adsorption process is exothermic, isothermic process. So, we can say del G will be equal to del H minus T delta S. Okay. So, where del G will be actually negative. Okay. So, then using this Clapeyron equation, we will be getting this delta H, that is well known one isosteric, will be equal to minus R T square d ln P by dt is equal to R into. So, if we enter this one inside this dt, so R into ln P by d 1 by T. So, this negative will be coming along with T square. So, we can say this d ln P will be delta H isosteric by R into d 1 by T. Okay. So, we will be doing one thing, say we will be changing the temperature from T1 to T2. Suppose if we plot now 1 by T, so differential 1 of the 1 by T. So, we will be getting like this, we can say. So, increasing the temperature, or we can say this one, if we decrease this 1 by T. So, we can say this one, suppose this is for T1 and this is for T2. So, for this we will be getting 1 P and for this one will be this P. So, differential of ln P will be plotting here, suppose ln P is plotted here. So, differential of ln P will give this one differential of 1 by T like this. So, this is, we can say this one for this is 1 by T1, this is 1 by T2. So, this is 1 by T1, this is 1 by T2. So, we will be getting that type of thing or straight line. The slope will be like this, delta H isosteric by R. So, from here actually we will be getting this R is the universal gas constant. So, we will be getting this delta H isosteric from this equation or from this experimentation. So, if we change the temperature from T1 to T2 and if we plot 1 by T1 versus to 1 by T2 and differential 1 with this differential logarithm pressure, we will be getting this we can say straight line, and the slope will give the we can say this enthalpy values, isosteric heat of adsorption process. Now, another important parameter is the selection of the adsorbents. So, there are 4 different we can say criteria like this ease of separation. If the relative volatility of component in a mixture is close to unity, then one specific component can be separated easily by this adsorbent, this adsorption process. Then solute concentration, a low concentration of target component in feed can be easily separated by adsorption process, because we have seen that the adsorption process is proportional to the partial pressure of the solute or adsorbate, as well as this it is dependent on the vacant we can say or active species. And process condition like adsorption is effective, product is susceptible to thermal damage, there we can say adsorption will be very effective. And these adsorbent criteria like adsorption capacity, mass or volume of the solute adsorbed per unit mass of the adsorbent also is very important. Okay, now we will be solving one problem, very simple problem, like the following data have been collected on equilibrium adsorption of the nitrogen on an oxidation catalyst at 77.4 Kelvin, the normal boiling point of the nitrogen. Then now we need to determine the specific surface area Sg of the catalyst by BET technique, where this vapor pressure is given that 760 millimeter mercury at 77.4 Kelvin. For liquid nitrogen, density is given as 0.808 gram per cc. Okay, so this is a very simple problem. For that, the pressure as well as this volume, these are given. Suppose this pressure is suppose 10 millimeter mercury, then volume is 71.3 this we can say centimeter cube per 100 gram solid. So, that way up to this 500 millimeter mercury pressure, the volume is given. So, we have this pressure versus volume is there. So, from there actually we will be getting all the other parameters for the BET surface BET this one which is adsorption isotherm. For that we will be doing, we need to get finally what is the SG value. Okay, so, we will be doing this one very systematically, we will be doing like this. We may be requiring few points, but for the betterment of the result we can do this one. Suppose this P, like this P is 10, then we say P by PV will be 0.0132 and say P by V into PV minus P will be say 0.0187. Like whenever we will be having this 20, then it will be like this 0.0263, then it will be 0.019. So, when it is 40, so it is 0.0526, then it is 0.0193. Okay, so, whenever the pressure is increasing to 100, so it will be like 0.1316, then this parameter P by V into PV minus P will be 0.0223. So, this way we can say for say let us say 250, we can calculate others also. For 250 that P by PV will be 0.329 and the P by V into PV minus P will be 0.028. So, like this one, if we say 400, we will be getting 0.5263 and the P by V into PV minus P will be 0.0322. For 500, we will be getting 0.6579 and this P by V into PV minus P will be 0.0364. Now, we will be plotting this one in the say P by V into PV minus P versus P by PV. So, now we will be getting one equation, it is a straight line. So, where actually we will be getting this, we need this slope. This slope will be actually from this graph. If we use this graph paper, then from there we will be calculating, but here actually we are putting this value 0.0249 and intercept actually will be equal to 0.0187. Now, we will be getting this this one, just now we have solved this one, that QM is equal to 1 by slope plus intercept. Okay. So, that is we can say this one 1 by slope is equal to 0.0249 plus intercept is equal to 0.0187. So, it is coming out as 22.94 centimeter cube per gram of this adsorbent. Okay. And alpha, that is we know this one, that is 1.09 into m by n into rho to the power 23. Okay. So, that is coming out as 1.09 into m is molecular weight is 28 for air and Avogadro number is 6.023 10 to the power 23 and density is given as 0.808 to the power 2/3. Okay. So, it is coming out as 1.625 into 10 to the power minus 15 centimeter square. Okay. So, Sg will be equal to Qm into N by V into this alpha. So, that will be coming out as 22.94 into 6.023 10 to the power 23 and into 1.625 into 10 to the power minus 15 divided by 22,414. So, that is the specific volume, actually this we can say molar volume. So, that is coming out as 1.002 into 10 to the power 6 centimeter square per gram, or we can say 100.2 meter square per gram. Okay, so, this Sg we are getting as a specific surface area 100.2 meter square per gram. Okay. So, thank you very much, and in the next class we will be discussing about stage wise and continuous adsorption process.